joining us today. I'm Ellen Aruda. I'm the Tim Manganello Borg Warner Department Chair, Mechanical Engineering, and I'm pleased to welcome you to the 17th Annual Michael Korybalski Distinguished Lecture. This lectureship was created to bring high-profile, inspiring speakers to the U of M community, to promote the impact of engineers on broader societal problems, including energy and the environment, health and the quality of life, national security, and disaster prevention. The U of M Emmy Endowed Lecture Series is made possible by Michael Korybalski, former chair of Emmy's External Advisory Board, distinguished alumnus, and former CEO of Mechanical Dynamics. So I'd like to take this opportunity to thank Michael for his generous gift and for making this event possible. Michael and his wife Phyllis are here. Would you mind? So now it's my honor to introduce the 17th Michael Korybalski Distinguished Lecturer, Walden C. Rhines. Dr. Rhines is the Chief Executive Officer of Silvaco Group, Inc., an electric design automation company, and Chairman of the Board of Qorvo, a semiconductor company focused on RF communications. He's also currently a board member of 3 private semiconductor companies, Kornami, Caspia, and Palladius. He previously served as the CEO of Mentor Graphics for 25 years and as chairman of the board for 17 years. During his tenure at Mentor Graphics, revenue nearly quadrupled and the company's market value increased by nearly 10x. Dr. Rhines earned his Bachelor of Science in Engineering from the University of Michigan, a Master of Science and PhD in Materials Science and Engineering from Stanford University, and his MBA from Southern Methodist University. He also holds honorary degrees, doctorate degrees in technology from the University of Florida and Nottingham Trent University. He's a lifetime fellow of the IEEE and has served on the National Advisory Board of the University of Michigan, the Board of Trustees of Lewis and Clark College, and industrial committees advising Stanford University and the University of Florida. Dr. Rhines has also been elected 5 times to serve 2-year terms as chairman of the Electronic Design Automation Consortium, the international trade association for the EDA industry. We're honored to have Dr. Rhines and are looking forward to his lecture, Engineering a Platform for Success in Diverse Pursuits. So, take it away.
And thank you, Michael, for giving us this opportunity. I did indeed graduate from the College of Engineering, and I am not a mechanical engineer. I took a number of mechanical engineering courses. I liked them. The interesting thing is I hardly took any electrical engineering or computer science, and yet I had most of my career dedicated to those areas. So I'm going to take you through a little walk through vignettes of history, because I think it says something about Michigan and Michigan engineering for why you could specialize in one area as an undergrad and a graduate student and end up making your living in totally different areas. But before I do that, I was actually asked to do a similar endowed lecture at Stanford University a few years ago, and that particular one was in honor of essentially a mechanical engineer, Bill. Bill Nix is. They have an annual lecture every year. And Bill has received just about every possible honor that an academic can receive. So I had to dig around to find out something I could say that would be at least a little critical of him. And I found something. I read the book by Walter Isaacson on Elon Musk. And these are exact quotes from the book. Musk planned to enroll at Stanford at the end of the summer to study materials science as a graduate student. But as he got closer to enrolling, he began to worry, I need to catch the internet wave. He actually hedged his bets. He officially enrolled at Stanford and then immediately requested a deferral. I've written some software with first internet maps and Yellow Pages directory, he told Bill Nix, the material science professor, exact quote from the book. I will probably fail, and if so, I'd like to come back. Well, Bill told him, if you delay your material science PhD, you will likely lose that opportunity forever. Nix said it would not be a problem for Musk to defer his studies, but he predicted that he would never come back. So Elon Musk went through life without a PhD in material science and engineering. Can you imagine how successful he could have been if he followed Bill Nix's advice? Oh well. So I did follow Bill Nix's advice. I did get a PhD in material science and engineering, and I'd like to introduce you to some of the influential people along the way. First, there was Craig Barrett, who was the principal advisor I worked with. Craig later became CEO of Intel, succeeded Andy Grove for quite a prosperous period at Intel. He was their youngest professor, and I did a thesis that involved a lot of electron microscopy. So Craig was very helpful, but he also had another attribute that was quite useful. He willingly paid for the beer at the Oasis long after the graduate students had run out of money. Well, there was also Gerald Pearson. He was one of five who developed the transistor at Bell Labs. He did not get the Nobel Prize. Brattain, Partine, and Shockley did. However, he is the sole inventor listed on the original silicon solar cell patent. And more importantly for me, one of his previous graduate students was Morris Chang. Morris, at the time I graduated, was the head of the semiconductor group at Texas Instruments, but later went on to found Taiwan Semiconductor, UMC, the largest semiconductor companies in the world. There were some student influencers, and I thought I'd throw one in from Michigan. Sam Fuller and I lived together in fraternity, and when it came time to go to grad school, we debated. Now, Sam was in high demand, so it came down to MIT versus Stanford, and of course we chose on very objective bases. Think of the weather, think of the women. You know, why would you go to MIT? So that's how we got there. Sam became the CTO at Analog Devices. He was the head of research and development for digital equipment. But most importantly, the indications were there early on. Sam had the highest grade point average in the class of 1968 in engineering, and it was a record, 10-year record, versus the last time someone had gotten that high in average. He had 1 2-hour B in engineering English. Remember engineering English? Well, yes, I don't think they have that anymore, do they?
They don't teach English anymore.
Okay. Then there was Herb Moraska. Herb and I shared an office at Stanford, and Herb had worked at the RCA labs, and they were paying for his graduate study. But they told him, when you go there, please invent the blue LED. Why would you do that? Well, the answer is there were light-emitting devices for green, for red, for other shades, but you really needed blue or violet, because you need all the wavelengths in the spectrum if you want to produce white light or anything else. And blue and violet were very elusive, but he had been introduced to gallium nitride, a 3,5 compound that has a very wide band gap, just sort of coming into its own in the last decade or so. So there was potential, because of the wide band gap, to emit higher frequency emission in a light-emitting diode. And so Herb was trying to do it and becoming very frustrated. I found throughout my career that the periods of greatest innovation are when you're desperate. Think if your basketball team has lost 3/4 of the games in a season, you're really desperate, and so you do something about it. Well, the same thing with Herb. And in fact, he did. We went to the laboratory, with his frustration, we sat down together and went through the periodic table, and we looked at all the possible elements that you could dope gallium nitride with. And we came across one, magnesium. And so, if you look at, I suspect, these lights, all the light bulbs in the world today are magnesium-doped gallium nitride. And Herb didn't get the Nobel Prize, but the Nobel Prize winners noted, I don't think my or the other two's work would have been possible without Mariska's contributions. In fact, the other two basically just reproduced what her did. Nakamura was the big innovator. After we got the blue light emitting diodes working, we filed and received a patent. The patent is 1974. It's a patent on the use of magnesium-doped gallium nitride to emit blue light. So you're thinking, wow, every light bulb in the world, Stanford must have made a fortune on this patent, right? Not quite. They didn't make anything because the patent has a 17-year life, and blue LEDs really didn't take off until long after the 17 years. But today, we're able to make white light because we have blue LEDs. And then there was Shang Yichang. You probably haven't heard of Shang Yichang, but he had the same advisors I did. And our advisor, Gerald Pearson, as I mentioned, was also Morris Chang's advisor. So when it came time to finish our degrees, Gerald just said, hey, don't even interview, I'll take care of it. I'll call Morris. Called Morris. We got all sorts of job offers from Texas Instruments. So we both went to work at Texas Instruments. But if you're wondering, how did TSMC move ahead of Intel and become the most advanced semiconductor manufacturer, you are looking at him right here. It was Shang Yi who ran the R&D for over 10 years. Shang Yi who took the risk to go to extreme UV, whereas Intel did not take the risk. He made the key decisions. He brought them into the forefront. Not as widely recognized as some, but really very key to where we are in the semiconductor industry today. And I used to kid him that, Shang Yi, every time I visit Taiwan Semiconductor, I look at your logo, and I've noticed you see on this is a wafer of silicon, and you see these black dots are defective die, because that's the way we used to mark defective die. And say, Shang Yi has an awful lot of 20 defective die. You ought to work on that. And so one year I went by, and sure enough, it wasn't just the engineers who improved the yield at TSMC, it was the marketing people. They got a new symbol in 2005. It had only 11 defective die, 50% improvement, and a much more easily read symbol. Everybody has to contribute. Okay, so I go to Texas Instruments, and the project I worked on was solid-state imaging. So at the time, the new technology was charged couple devices, and the way those work, you shine light on the silicon, and it generates electron hole pairs. Those diffuse under the electrodes, and then you can clock them out, and it produces an image, just as your cell phone does today when you take a picture. But, once again, TI was in a fairly desperate stage, so we had to do something innovative. So everyone else did the straightforward thing that you shine the light in on the device and you get the image. He said, wait a minute, why don't we thin the devices to about 20 microns thickness, and then you can shine the light in on the backside. Then you don't have all the interference of the device structure. And it turned out the Department of Defense, the Night Vision Lab for the Navy, was very interested in this because they were making starlight scopes back then, and they needed something that would not have the interference of the device structure. So we did it, and it was successful. The problem, like the previous one, is it wasn't until about 20 years later that it actually made it into commercial practice. So if you look at your cell phone today, it's backside illuminated. Finally, it was adopted around 2000, 2005. But in the meantime, we sold a bunch of contracts to the military, and then they finally said, it works, it's fine, we're done, no more funding. This is a real problem if you're living off a specific technology with specific agencies of the government. So there are only about 6 or 7 of us in the group. It's the R&D labs at Texas Instruments. And one of them, Larry Hornback, said, well, what is the government funding now? And Dean Collins, who was head of the group, said, well, look, everywhere I go, they want heads-up displays for pilots. It was the new thing. But that's the opposite of an imager. You're detecting an image. Heads-up display, you have to project an image. So we didn't really have anything, but Larry, being very clever, said, wait a minute. When we thin these things, if we could do it and divide it up into pieces, we could make little mirrors that would reflect light. And if you twisted them, you could turn them on and off. That would work really well. And so he went in the lab. He did it, a 3x3 array. And it took 20 more years to get up to high resolution, but ultimately that became the digital light processor for Texas Instruments. And it became more than $1 billion business. But you all have been exposed to this if you've ever gone to a movie theater. Because before the DLP, movie theaters received their new films came on acetate. They were actually really reels of film. Today, they ship compressed video over the internet or wherever, and that makes it up. And so as a result of that application, Larry won an Academy Award and was honored for his innovation in simply taking something we were doing because we were desperate and creating a new application. Well, meanwhile, I'm looking at the annual reports of Texas Instruments, and there are 35 vice presidents, and I discover that not one of them has ever managed a wafer fab, run silicon manufacturing, and here I am doing silicon process development. Well, this is not a good place to be if there are 35 vice presidents and none of them have ever done what you're doing, so I decided to get into design. So I managed to get it assigned to a design project and learned a little bit about design, not very much. But fortunately, the company had a consumer products division that mostly made calculators. And it was growing so fast that they decided to move the business from Dallas to Lubbock. Not really a very good move. Now, my friends from England said, hey, Dallas, Lubbock, what's the difference? It's all on the frontier. But the people living in Dallas really didn't want to move to Lubbock. So all sorts of jobs opened up, including engineering manager with like 150 engineers reporting to me. In fact, it's my only mechanical engineering. We had 150-ton presses that did injection molding of plastics. And we had to design the cases and get someone to do the tool and die work. But mostly what we did was design chips. About 30 different custom designs a year for all the calculators we introduced. And by the time I got there, we had gone from very popular data math calculator with 480 components, sold for about $300, and they had gotten it down to 50 components by 1974. So the challenge, like putting a man on the moon, was let's do a single chip calculator. Seemed impossible, but in fact, we did it. Got the single chip calculator, later got the single chip scientific calculator, and once again, you'd think we probably made a lot of money. The answer is no, we didn't. There were Japanese manufacturers who quickly followed. They could produce the calculators more cheaply, and especially for consumer calculators, add, subtract, multiply, divide, the competition was too much. We were losing so much money that, in fact, we finally just decided to relabel the Japanese calculators and sell them. So you can see the similarity here. This is a Toshiba calculator, and here is the TI one with the TI label, and that is the only difference between these two. We were able to sell them for $3 more than Toshiba could. Same thing here, but that's not really a terrific business. But we did have one product that was really surprising, I guess you would say. It was called the Little Professor. And it would flash an arithmetic problem up, and the child would enter an answer, and it would tell you whether it was right or wrong. And we always expect the calculator model to peak and decline over about a 5-year period, but the Little Professor just grew every year. And we finally figured out that parents will pay almost anything to help their kids in school. So Paul Breedlove, out of desperation, his group is losing so much money, he says, wait a minute, why don't we teach spelling? Well, there's a little challenge there. The challenge is that you've got to say a word so the child can spell it. And the problem with saying the word is at that time, synthetic speech, electronically generated speech, was not viable. It just required such demanding performance for computation that it couldn't practically do it. But of course, we didn't know that. And Paul attended a presentation in the research labs where they had compressed speech down to 1,000 bits per second. Sort of understandable, sounded like a robot, but anyway, but there was another issue. Consumer products have to be affordable, and so we had to get the cheapest possible. We were not part of the semiconductor group, so we're always negotiating price, and Morris Chang was head of the semiconductor group, and he got tired of arguing, so he finally said, $20 a wafer, that's it, and that's for the cheapest, the oldest, the slowest technology you can buy, because that's what we used. You know, hey, it had to be cheap. And so Larry, this guy, didn't know any better, and he designed a pipeline multiplier to do linear predictive coding, basically digital signal processing, on the slowest, the cheapest, the oldest technology, and it worked. And so Speak and Spell was introduced. At the time, the management wanted to shut it down because they told us for sure any consumer product that costs over $40 requires both parents to decide you'll never sell it. We introduced it at $60 and we raised the price and we're sold out for a couple of years. So big success. And as a result, as I left consumer products, TI started to say, hey, this is a really tough business. Let's specialize so we won't lose so much money. And so they said this education market is really a place to go. So they specialized just in education. They lobbied school boards, they prepared courseware, they trained teachers, they gave out prizes for schools and for teachers and so on. And the business narrowed its focus. Now this is the TI-89 titanium graphing calculator. Now, having raised two daughters through grade school, junior high school, and college, I have personally purchased 8 of these calculators. They lose them. They break them. They loan them to friends. Well, the net result, I knew that TI outsources these to a manufacturer in Asia and does it for about $30 or less per calculator. So the margins are pretty extraordinary here from having that focus. But the schools were, oh, you gotta buy the TI calculator, and so we had a great market. And so TI continued to report their consumer products division, P&L, separately in their annual report. And by the time we got to the year 2000, they were up to 50% gross margin. By the time they got to 2007, it was 65% gross margin, at which time they stopped reporting the consumer products as a separate segment. Now, I can't prove this, but having been a senior manager at TI, I'm going to assert that the reason they stopped reporting it is because the numbers became embarrassingly good. That is, 65% gross margin is far greater than they get in their primary business of selling semiconductors. So why advertise that you're not making much money in semiconductors and you're making a boatload of money in this billion-dollar consumer business? So they stopped reporting it, but I guarantee you it is a big contributor to TI's profit today. Well, here I am. I'm located in Lubbock, Texas. I'm almost 30 years old, and I've got a good, responsible job, but my principal objective at that point is, how do I get out of Lubbock, Texas? So, another opportunity comes along. It turns out that Texas Instruments has been the king of semiconductors from the time I joined because of bipolar digital logic and linear parts. But so the generations of bipolar digital logic, RTL, DTL, and TTL, TI dominated TTL. And so the big three of semiconductors were TI, Fairchild, and Motorola. TI had 38% market share, The three companies together had 3/4 of the whole semiconductor market, very concentrated. But as the industry shifted to MOS, metal oxide semiconductor, then the battlefield changed. Fairchild never made the change at all. Motorola struggled. TI made it, but wounded. And so 16-bit microprocessors come along, and we have a number of candidates. We have Intel with the 8086, Motorola with the 68000, Zyla with the Z8000, and TI got in early with the 9900, but the employees of Texas Instruments knew full well that the 9900 was going to lose. I mean, it was only 16 bits of logical address space compared to 20 for Intel and 24 for Motorola. And there was this group in Boca Raton, Florida, a division of IBM, just a tiny group that was doing this design. They couldn't say what it was. No one knew what it was, but we all went. We presented to them and presented why they should use our microprocessors. Now, their hands-on choice was Motorola. I mean, Motorola was everything IBM wanted. It was a big Indian, like all IBM computers, that is byte order, the one byte first versus the other. Intel was a little Indian. It was 32-bit internal architecture, 24-bit logical address space, everything they wanted. And here we have the TI 9900. Now, IEEE Spectrum asked me to write this article in 2017. I didn't know they were going to title it Texas Instruments' Biggest Blunder. I might not have agreed to, but anyway, TI had the 9900, and that's why nobody wanted to be head of the microprocessor division at Texas Instruments, because they knew it was going to be nothing but grief. Unless, of course, you had another goal, which was to get out of Lubbock, Texas. So I took over the microprocessor group. And we did, before I got there, we did something that seemed like a smart idea. I decided the reason the 9900 wasn't selling was because there were no peripheral chips that went with it. So there were lots of peripheral chips for 8-bit microprocessors. So let's just put an 8-bit bus on the 9900. Well, it sounds like a good idea, but then you ended up 8 bits to load the instruction, 8 bits to load the data. It ran exactly half as fast as the 9900, which made it no different from the 8-bit microprocessors, which made it not very compelling. But Jack Karsten, who was head of the MOS group at TI, left during this process and went to become head of Intel marketing. And he still thought it was a good idea. So Intel did the same thing. They put an 8-bit bus on the 8086. And so the net result was they had a total dog, we had a total dog. This IBM group comes out and says, I need a really low price and I'm going to buy big volume. Nobody knew this was the IBM PC. And so Andy Grove at Intel says, hey, I am not selling the 8086 for that lower price. Tell you what, offer them the 8088 for whatever they want to pay, because we've never sold it to anybody else. And son of a gun, IBM took it, which is why today you struggle with the PC architecture that is built into your computer, because Motorola could not yet pass an IBM qual. They didn't have production release parts. If you haven't been through an IBM qual, I mean, you have 1,000 PhDs descend upon you and run every possible test. And you have to have stable manufacturing. So Intel won with the 8088. And bad as the 8088 was, the 9900 was even worse. So it made history. But it left me in head of the microprocessor group with a known failure in my path, and the management fortunately had basically given up on the microprocessors based on what was happening and then the announcement of the IBM PC. So that's good. I found once again, desperation spawns innovation. And so we said, hey, what comes after host microprocessors? Let's look to the future. So, hey, special purpose microprocessors, right? So we designed one for communications, one for graphics, one for mass storage, and one for local area networks. Now subsequently, this one for communications, the TMS 320, was so successful that it became over half of TI's total revenue along with its derivatives. So massive success. And you must think, oh wow, that was really brilliant. How did you figure out that that would be in such demand? I mean, first of all, the It's a problem. The cultures of our companies would indicate this was not very logical at all. Motorola had grown up with mobile communications, car radios and things. TI had grown up as a computer company. They were in the oil exploration business, digital seismic data analysis, where you had to analyze big volumes of data. So they had developed computers, and so basically, TI was a computing company and a semiconductor company, and Motorola was communications and the second largest semiconductor company. So you say, why didn't we develop a computing one and Motorola the other way around? And the answer, when I talk to senior managers, they always say, oh yeah, the divisions of our companies, they work so well together, they help each other, their products, they share information, and all the benefits of having multiple divisions in a company. My experience is that is rarely the case. In fact, the divisions normally compete with one another. And so, it's not illogical that TI should develop the premier processor for communications, and Motorola should develop the premier processor for data processing. And in fact, we designed the Motorola 68000 into our mini computers as a standard, and Motorola designed the TMS-320 into their cell phones as a standard, and we all could live a much happier life than if we had our management expediting us to sell to our sister division. So, must have been a well thought out product spec, right? So, the planned markets for the digital signal processor, we were building upon our speech experience, so we had lots of test algorithms to test. And when you're doing digital signal processing, you want to be very efficient at things like discrete cosine transforms. And so we defined the processor to do on-chip hardware multiply, which was its distinguishing feature. And in fact, modems were an obvious thing to do. But the reality of the actual volume that made this generated billions of dollars of revenue was, in fact, transitions that could not have been anticipated. Disk drives were analog, and as disk drive companies wanted to compress more data onto a disk and to improve the performance, they had to go digital. And so all the disk drives in the world sort of overnight switched over from analog to digital. TMS-320 became the standard. Cell phones were all analog. At the time we defined the chip, we didn't know they were going to turn to digital, and yet digital baseband for cellular, when you sell 1.8 billion cell phones a year, and TI had 55% of the market, that has a big impact. So, big success out of total ignorance, but a lot of desperation. And then, Data Systems Group. So I ended up as president of the Data Systems Group, and at that time, sort of the same problem. It was not that bad a business. It was $500 million a year of revenue, selling mini computers, printable printers, portable terminals. The only problem was it used to be $1 billion business, and when I took it over, it was $500 million and on its way to zero. So we needed to find something differentiated. You may have noticed the jobs I've taken have all been pretty hopeless. I'll show you another one in a minute. But for this one, hey, we need something differentiated. What can you do that's differentiated in the computer business? I've got it. Artificial intelligence, right? Of course, why not AI? So, here this is 1986. It says, artificial intelligence, heavyweights get into the act, meaning Texas Instruments. So, I think if you look carefully, you can see my smiling face there. Surely I don't look any different. Good. It's 1986, that was a while ago. Anyway, so we tried this as a business, but there were really some challenges. First, actually in 1986, while we were ahead of the game, there were others who were even further ahead of the game. And the Dartmouth Research Project in the summer of 1956, 30 years before it, had come forth with projections like, within 10 years, a digital computer will be the world's chess champion. Close, not 10 years, 60 years was the reality. Okay, well, Marvin Minsky, who founded the Artificial Intelligence Lab at MIT, he said, in from 3 to 8 years, we'll have a machine with the general intelligence of an average human being. Well, I think that says more about the general intelligence of an average human being than it does about AI. But we had a movie, 2001, A Space Odyssey. Some of you may remember it. And there, the computer could communicate through natural language speech back and forth with the crew. But the computer found out the crew was doing things it didn't want, and so it had to terminate some of the crew. So the movie could not attribute that to IBM, the leading computer company at the time. So they moved the letters, one letter to the left in the alphabet from IBM, and called it HAL. Very successful movie with HAL 9000. And so if we move forward to 2001 and think about these computers that behave like humans, where were we? Well, in 2001, we had developed neural networks that could distinguish cats from dogs. A little short of the expectation. There were some reasons. First of all, we didn't have big data to analyze. There was no internet. We had limited computing power in terms of being able to process the kinds of algorithms you would need for neural network training and inference. We needed more advanced algorithms, lots of things developed. But most of all, we needed killer applications, some way you could make money. And we really didn't have any at that time. But one by one, these barriers disappeared. So we get to the near 2020 period, and we find ourselves with applications emerging. So I was asked to give a speech about maybe 5 years ago, at least 4 years ago, about, hey, it looks like NVIDIA's running ahead, but AMD's got a processor, and Intel, and Microsoft, and we've got Google with the Tensor products. How's this all going to shake out? So what I did was to listen to the earnings calls in one quarter for all the companies, and then I plotted the number of times they mentioned the word AI during the earnings call and compared that to the 12-month increase in stock price. And I found out NVIDIA won hands down 107 mentions of the word AI. Can you imagine that in a 30-minute call? They said AI so many times that it became obvious to me they would be the winners, and they were. Well, so far they are. Okay, so now we have the next phase of life. The CEO of Texas Instruments told me, hey, you're 47 years old, and I got to tell you, I'm going to be in my job for another 10 years. So forget about a promotion. I'm running the semiconductor business, which is now the only business at TI. And so he said, as long as you don't go to a competitor, I won't stand in your way. Better if you stay, but I understand. So I couldn't interview for a job. I could just respond to desperate companies who inquired. And the most desperate of them was a company called Mentor Graphics. Mentor Graphics was the original real electronic design automation software company, and quite successful, but they had past their prime. They had missed a whole generation of product development. And so they were pretty desperate. And unlike most calls I got, they were going to replace their CEO. Most companies would call and say, hey, our founder and CEO wants to take it easy, and will you come in as COO? And I found that's not a very good formula, but to come in and just take over sounded okay. Of course, the company was running out of cash. And most times you think when you change jobs or you get a job, you want to go somewhere where the company is doing well, where there is growth and growth potential for the future, where they have adequate funding and good investors. I've actually found that if you do that, no one is ever going to know whether you did anything for the company. Because if you're lucky, it'll continue on that growth trend, and everyone will forget that you joined it it's all downside. Whereas if you join a company where everyone assumes they're going out of business, they're in desperate straits, if you do anything, it will be viewed as a success. And Mentor was. So, Mentor, sort of desperate. Here's the, 20 years of revenue for Mentor Graphics, reported numbers. You see the revenue. They had peaked in 1990, and that was the peak. Then they decided to introduce a whole new generation of software. They were unable to ship it, so they started on this downward path, which most people assumed would do this. So, excellent timing. I joined the company in 1993, and while it was unpleasant for a while, it in fact did grow. It grew at a pretty modest rate, 6.6%, although in later years it grew at 9.2%. It ended up being a reasonable success financially. And it's a business that's sort of unique. Electronic design automation software is very specialized. The number of designers in the world doesn't change very fast. And so you've got three big companies that constitute 75 to 80% of the total revenue. In this case, Mentor, Cadence, and Synopsys, but it used to be Daisy, Mentor, Valid, and before that it was Calmavision, Applicon, and forgotten who else. Anyway, the net is within that. There are specialties, special types of software that different companies are very good at. So in this slide, we show in blue is the #1 supplier to each of these segments, like logic synthesis and place and route and design rule checking and so on. This one is the average over the all of the segments of EDA that are more than $1 million a year of revenue. What you see here is the #1 supplier has 72% of the market and a minimum of 40%. I guarantee you, if you have 70% market share in anything, you will make money. And so, all you have to do is figure out where there's a weak point, where there's a new emerging technology. So we found a couple of them, and so it drove the company forth. So you'd say, oh, wow, must have been really great. That's why you stayed around for 25 years. No, actually it wasn't that great, because every once in a while you have a bad quarter, and it's not very pleasant, and your investors get very unhappy. But worse yet, people come after you. Cadence, 2009, larger than we were. We had a bad quarter. Cadence comes in with an unfriendly takeover offer. Fortunately or unfortunately, they were unable to consummate it because they couldn't raise the money. Well, there's a guy, Carl Icahn, who's an activist, who looks for situations like that and figures, aha, they fought off the unfriendly acquirer. It must be that Wally is trying to protect his job. I'll just go in and make sure they do a deal. So in comes Carl. Carl, well, we end up with a proxy contest. Carl ends up with 3 directors out of 8. Not a pleasant thing to manage a business like that. And that Christmas, Carl sent me a bottle of scotch that said, "Not for use at board meetings!" exclamation mark. Cheers, Carl. So, a little tough for a couple of years. And then stock goes up, actually triples. Carl triples his money, makes an extra $500 million, and the bottle of scotch that Christmas was to be used at board meetings. Cheers, Carl. So we had it free for a little while, but then not long after that, along comes Elliott Associates, one of the largest private equity companies in the world. They spot value. They decide they're going to do a takeover. And so, fortunately, one of my board members was very close friends of the CEO of Siemens, Joe Kaeser, and he said, hey, Joe, you ought to buy this company. It's really good. And they did. So Siemens bought the company, $4.5 billion, and that happened in 2017. And then Siemens is worried about the transition, worried about keeping the employees and so on, and they say, how would you like to become CEO Emeritus? Now, if anyone ever offers you the job of CEO Emeritus, take it. I mean, this is the ultimate in jobs. You get paid, you travel the world and give customer presentations, you meet with the customers, you have a great time. But I knew this will not go on forever. And it didn't. It went on for a few years. In the meantime, I started pursuing some other things, startups, and I'd never done a startup, and so I was on the board of a couple, and I did something that Mike also did. I went and did some work for DARPA, the Defense Advanced Research Projects Agency, and they introduced me to a very critical technology for the government called homomorphic encryption. Now, fully homomorphic encryption's been known about for a long time, but fully homomorphic encryption was actually developed by a graduate student at Stanford University in 1989. And it's really pretty remarkable what it does. Compare this. Today, when you're on your PC, you enter your password, you bring up your bank account, you enter some data, you press enter, and your computer in the background encrypts your data, sends it to the cloud. In the cloud, the computer has to perform computations, so they decrypt your data. How do they do it? Well, you send them your password. You send them the key so they can decrypt it, and then they compute on it, and they re-encrypt it, and they send it back to you. Well, that has some real deficiencies. Your data is floating around unencrypted in a data center that can be hacked into, and worse yet, you've given your key away so that anybody who gets that key can decrypt anything from your computer. This is not good. So, what is the ultimate in security? The answer is homomorphic encryption, where you press enter and your computer encrypts the data in a very secure form of encryption, believed to be resistant even to quantum computers. No one's figured a way to break fully homomorphic encryption. They don't expect to. It sends it to the cloud, and then the computation is performed upon the data while it remains encrypted. Nobody has a key. It computes on the encrypted data. Really remarkable, and sends you the result, and you have not given away your key. No one has ever seen the plain text data, so no one can steal it. It's pretty darn good. Why doesn't everybody use this? I mean, there is a problem. The problem is it is computationally unbelievable. So, 4 bytes of data when encrypted with homomorphic encryption goes to 1.7 megabytes. A single CPU operation on plain text data now requires 12 million CPU operations, and there's a bunch of overhead on top of that. So an application that can be done in 1 second on a normal computer now requires 11 days on that same computer to compute on the encrypted data. Wow, this is a real limitation, but not for innovative people, right? People have been improving upon it ever since it was developed. So these are all software improvements of 8 orders of magnitude improvement in performance, but we're still 4 to 6 orders of magnitude short of what we need. Well, maybe NVIDIA will solve that problem. The answer is no. NVIDIA will not solve that problem because data movement in von Neumann architectures, which is what Intel and NVIDIA use, is terrible. It's a von Neumann architecture. You load the instruction, you load the data, you do the operation, you go back to memory. It's always going back and forth to memory. It just has bottlenecks for moving data through quickly. And so what happens when you add processor cores, as Intel has done, as NVIDIA has done, and as you add the number of cores, you get a little increase in performance here, or a big increase, but then the more cores you add, the more it slows down because synchronization and memory bottlenecks and all the accesses to memory that undergo contention. So the answer is there is no solution with conventional architectures. What you have to do is a new architecture. One that has been known a long time is data flow. Data flow has no ALU, it has none of this memory stuff. Basically, the data streams directly in the processor. But you have to have some way to compile the data so you can stream it. If you do it right, which no one has to date until this, You can divide an application up into independent streams of control and data. If they are totally independent, then if you want to double the performance, you just double the number of processor cores because they run totally independent of one another. So in principle, you can have unlimited performance, just throw more processors at it. That's not true of von Neumann architectures. It's not true of all the other architectures around. But we had a compiler, that's what the company was founded on, that could compile any application into independent streams. And we designed a chip that was what we call a share nothing architecture. So each processor core could do everything every other core could do. Each one had local memory, so it would scale linearly. And so with all these cores, we were able to put 2,000 cores per chip. And so the company was called Korybalski, for a tsunami of cores. And right now, we have chips, we are shipping servers, and we've run out of money, but hey, we've done that before, so maybe we'll make it through. But anyway, it has other unique values, and one is parallelization. So in recent years, you couldn't depend upon Moore's law anymore, so what you had to do was do more processing in parallel. NVIDIA uses one form of parallelism called single instruction multiple data. Do the same operation on a whole bunch of data just like your any raster display does. There are actually 55 forms of parallelism according to Patterson and Hennessy, and if you can do all 55, then you have enormous opportunities for making more efficient, lower power, higher performance. We can do all 55. So you have massive parallelism. We can do millions of simultaneous concurrent operations. And then we have a very small footprint for each core. So at 16 nanometer technology, we're able to do 2,000 cores per chip. Well, think about what this does. This revolutionizes the ownership of information. It allows you to share information without ever showing the information. You're only sharing the encrypted data. You're performing the computation on the data while it remains encrypted. So let's say you have a valuable database. So one of the customers is a bank, and this is actually they're head of a consortium of banks, and they're not allowed to share data. They want to look for money laundering and fraud and other things, but they're not allowed to divulge the data. But they are allowed to divulge the homomorphically encrypted data because they're not giving anything up. Nobody can ever see the data. And so they do that, and then they run the computation, and it finds cases of fraud and money laundering. Same thing's true for medical applications. You don't want to share your medical data with everyone in the world, but we need larger medical databases. Well, you can share your encrypted data if you're sure that no one will ever see it, and in fact, that's what's happening now. We have mechanical engineering applications, company Applied Materials. Wants to help people improve the performance of equipment to get better efficiency, better throughput, lower power consumption, and they can do that if you allow them to see your manufacturing data. But as a semiconductor manufacturer, I would never let Applied Materials see the sensor data from my equipment because it would immediately go to my competitors. But if that data is encrypted as it comes off the sensor, then hey, they can share it, they can compute, they can do whatever they want. So all of a sudden, people who own valuable data, financial data, now can sell it again and again. No one ever sees it, and when they run the query, they get an answer back that's encrypted, and then you go and ring the cash register and charge them for the key to unencrypt their data, and they never see the plain text data. There's another reason for homomorphic encryption, and that is that almost all of the data on the internet is going to be subject to hacking by quantum computers sometime within the next decade. When they get to more than 10,000 sustained qubits, the quantum computers will be able to break everything except lattice-based encryption, which fully homomorphic encryption is the principal form of lattice-based encryption. So, sounds exciting, huh? Well, let me close with some words of wow. You didn't take any electrical engineering, you took a 1-hour computer science course along with Mike, I think probably the year after I did. And so you ended up, your whole life was, electrical engineering and software and other things. So what was it about Michigan? My father was a professor. He actually chose Michigan, said, look, it's the best undergraduate program in the world. And so, I can say from experience, and I've talked to a lot of others, whatever engineering specialty you study in college, you're probably going to do something totally different for at least a large part of your career. Michigan engineering provided something that I think was uniquely valuable, and that was problem solving. Learning, how do you make good assumptions? How can a problem be simplified enough to be solvable? Are the answers reasonable? And then, how did Michigan do it? Hey, hundreds of problem sets, cross-disciplinary courses, practical lab courses, and great professors. And I might add that at the time, Mike and I were starting out, there was a new thing called digital computers, and it was just like AI. Hey, this is going to replace all this stuff you're doing in engineering school. It didn't. It became an aid. It became something we could leverage to use our engineering skills to solve problems. So, is AI going to destroy the value of your degree? Commoditization from AI is going to change a lot of things. Anything you do that's routine, standard calculations, unambiguous problem solving is at risk. It's going to go away. But there are some preserved values, problem framing, system level thinking, domain judgment, experimental work. You're not going to allow the application to sign off on a specification or an end product. It's not going to communicate well with other engineers. So I think the engineers who will gain the most from AI are those who do have a good understanding of the underlying physics and constraints. They can rapidly iterate with AI tools, and they know how to validate and de-risk the results. So, what would I do? Well, first of all, learn the fundamentals. You can't get out of that. Practice verification and validation, not just getting answers, but reasoning about those answers. Get project experience. Deal with problems that are messy and ambiguous. Learn to use the AI tools, particularly because they can be such an enormous aid. They're revolutionizing the way we're doing product development, and build communication and collaboration skills. So I wanted to close, wanted to get a picture of myself back when Mike and I were undergraduates here at Michigan. I didn't have one convenient to me, but my wife and I were invited to a 1960s party a few years ago and had to dress up. And this gives you some idea of what I look like as an undergrad. Thanks very much.
Do we have any questions?
Yeah, I'm glad you brought up AI, and you're now CEO of a, you're now CEO of a, you brought up AI, and there's been a lot of changes in the last, say, 12 to 24 months, a lot of angst in some cases, and you're now heading up a company where you have to do development and that sort of thing. How much are you using AI in your present company, and how was it different than maybe what it was 12 months ago, and how will it be different 12 months from now?
Yeah, amazing. The last 12 months has been the most remarkable change I've seen in my whole career. In developing products, we about 6 months ago started using Claude. And pretty soon, people figured out the impact, so more and more of them used it. So now, everything is done with Claude. And things that used to take months now take hours or days. I even had a demonstration. We develop intellectual property that is design blocks. So you take a specification like PCI Express or I-Cube-C, something like that. You feed in the specifications of the end product. Claude will generate the Verilog associated with it. Claude will generate the test bench. Claude will run the test bench, find the bugs, and then Claude will fix the bugs and output production-worthy code. The software we've been shipping to customers for over a decade, we're now screening with Claude, and Claude is finding bugs that have existed all that time that we didn't know about. I think it's absolutely revolutionary, and I think you can sit back and say, wow, I'm not going to pay an engineer $200,000 a year to code. I mean, why would I? Claude can do it better, faster. All the engineer's doing is looking to see if Claude got a reasonable solution. I think the answer is we haven't laid off a single engineer for that, because now we figured out they can do 2, 3, 4 times as much work in the same amount as in the past. So I think the answer to your question is this is one of the periods of most revolutionary change for business. It's also one of risk. Think about it. Now, the people who use our software to design chips, and we've been selling them these pre-configured blocks to put in their chip. Why do they need us? They can just go get Claude. So it's a little scary in some ways. I think the dynamic will change. The reality, the stock market did a big sell-off of software stocks because they thought, oh, all the software companies are going to have competitors who just reproduce their software and introduce it. It's not the way the industry works. If you're a company and you've been using Salesforce.com and somebody comes in and says, I can do the same thing, that barely gets you through the door. You've got all of the problems of validating your database and proving they can do what they say they can do and all that. I don't think it's going to be that destructive, but it will change. I think the biggest thing is the drudgery, the hours at midnight you spent trying to find that last bug, the things you had to do for verification that were just running test bench after test bench. You're not going to have to do that anymore. I think engineering is going to get a lot more interesting.
Yeah.
Okay, go ahead.
Yeah, I just want to talk. You gave a couple examples of these sort of 20-year pipelines earlier in your talk about discovery to actual impact in society. You've seen that transition multiple times too. I'm wondering, what role manufacturing, plays in that journey in terms of we know how to do something, but we don't know how to make it, or we don't know how to make it in a cost-competitive manner. And especially given the loss of manufacturing leadership and know-how in the United States, how that sort of puts us at risk of being able to pass through those 20-year pipelines in a leadership position.
Yeah, it's a very interesting issue because people change faster than capital investment. And so if implementation of manufacturing requires new equipment, automation of equipment and so on, you can only do that as fast as you can raise the capital to retool the industry. And there's a thing called the learning curve, which says once you have gotten down the learning curve, you are more efficient, lower cost than anyone who is not as far down the learning curve. So the problem you point out with the US, thinking that you could just build a factory in the US and it's going to run with the same efficiency as the factory in Taiwan. I mean, TSMC did that. Their average costs in the US are about 50% higher than they are in Taiwan. I mean, hey, they have thousands of engineers who've been developing this stuff for decades. We're hiring new college graduates, few of which are trained in manufacturing. This is something that takes time. But retooling the capital base takes even more time. So I think you have, as you say, from concept to economic reality is a long path, and any one thing can slow it down. And the deployment is probably the one that is the slowest. Anything else? Oh, yeah, right.
Yeah, on the multiple FIG encrypted databases, that's specifically the software that you guys are working in, right? To allow to do these queries, and are there competitors working on this that are fighting you guys to do exactly what the chip guys were doing 30 years ago?
Great, great, yes. So, two issues. One is there's software and there's hardware. Software, it's pushed it, been optimizing since 1989. Now, it turns out the lead guy who invented it, Craig Gentry, works for us now. So we're able to work on the software as well as the hardware. But you're not going to get the 4 or 5 orders of magnitude left unless you do the hardware. And so you say, well, are other people doing this? The answer is yes. There are probably half a dozen companies that are developing hardware. None of them have tried to take on the task of fully homomorphic encryption, where you take any arbitrary computer program and you accelerate it. They are looking at the algorithms within fully homomorphic encryption and designing hardware to accelerate fast Fourier transform, for example, as a subset. There's a company called Niobium that has a chip, and it improves probably 2 orders of magnitude over a conventional computer. There are, Zama is another company that has used field programmable gate arrays to get some acceleration. But really, you've got to get close to 1,000,000x to make it everyday painless, to make it same cost, same performance as plain computing. That's what we expect to offer. We just need another round of funding to get there.
So we have a reception outside. There's time to interact and ask more questions then. Before that, though, we have a thank you gift for you. And Mike, do you want to come up as well? So, is this again?
Yes.
Yeah, so,
A word of warning, I learned this the hard
I
way.
know.
They are not coupled.
so it's, we have,
You hold that.
yeah, and then I think,
Oh, I think there's a picture of Vicky circling.
yeah, and then we have some branded swag for you.
Okay, let's do this. We can probably figure this out.
Then I'll come over this way. Oh, this.
Falls now, it's not my problem.
I should know not to touch.
Great, thanks a lot.